let's give the stage to Sebastian Mizera from the Institute to tell us about whether a positive space observables double copy.
Okay, thank you, Enrico, and thank you to the organizers for organizing this wonderful workshop. It's a pleasure to be here. And today I wanted to talk about asking this question that I've been thinking about for some time now, and we can already, it seems, begin to answer this question in two different setups. So the setups that I wanted to talk about today are, the first will be about the cosmological wave functions. So that's based on a paper that we've put out recently with Lawrence Eberhard from the IIS and Shota Komatsu from CERN. And then in the second part of the talk, I will be focusing on different observables, which are CFT2 correlation functions. And that's based part of the work in progress with Ruth Brita from Dublin, as well as Carlos Rodriguez, who's a talented student of Oliver Schlotter at the Uppsala University. Okay, so let me start with the cosmological double copy. So the order zero question that you should be asking yourself is, well, what are the right variables for this double copy? So recall that in flat space, we have this usual representation, and let's just recall some of the things that we usually take for granted. Okay, so we have a sum over trivalent diagrams, and that sum is a rational function of our momenta, polarization vectors, colors, and other things. We also have the masslessness and transversality. So these are these constraints. And everything is supported on the momentum conservation. It's so obvious in flat space that we usually don't even write it down. And lastly, everything, at least in the basic sort of Young's gravity setup, is dimension agnostic. By contrast, even the simplest wave functions are already complicated. So here, let's say we consider some wave functions of three massless scalars in four-dimensional de Sitter space. And if you actually compute it, you get some answer. It doesn't matter what that answer is. I just wanted to flash you that in principle, it can have branch cuts, it could have some discontinuities, and all that is effectively because of the fact that we no longer have energy conservation, we still have momentum conservation, which buys us a lot, but not quite that much. So what I think is that it suggests that momentum space is not the most natural way to express cosmological double copy. And instead, we'd like to propose an alternative representation. And that representation is going to work in the position space of de Sitter spacetime in arbitrary dimensions. So de Sitter will be in d+1 dimensions. And just to remind you briefly how it works is that we carve out some late time surface, which is d-dimensional. On that surface, we have some operators. And in the bulk, they interact via some Lagrangian, and we'll assume that all the fields in our talk are massless. So in particular, their conformal dimension has to be equal to d. Okay, so these operators have some positions x, as well as some additional variables, which could be polarization vectors and such. And I will denote a wave function with this symbol. So one thing that you can do is express that correlation function in embedding space. So basically, you embed your de Sitter space as some hypersurface in d+2 dimensional spacetime, just flat. And to that end, you can introduce these variables. Here, capital X for each particle I with some index A is going to be this d+2 dimensional vector, depending on the positions of the punctures of the particles. And similarly, we can introduce Z vector, which in addition also depends on the polarization vectors here. Okay, so that's the working embedding space is something that is very familiar to us from the CFT literature. So in those variables, what you can do is you can introduce these conformal generators, D. So these generators are operators acting in these X and Z variables. And similarly, you can introduce these combinations, which I will call just polarization tensors, which are just anti-symmetrized versions of X and Z. If you didn't follow that, the only thing that we actually will care about for the purposes of this talk is that they satisfy these conditions that D operators, they square to 0. Similarly, the epsilons square to 0, and epsilon.d's are vanishing as well. And in addition to that, we have a word identity, which tells us in this language that the sum over all conformal generators acting on our wave function gives us 0. So this is very reminiscent of the type of variables that we have at our disposal in flat space. And the way you should think about it is that we should replace the momentum vectors from flat space into these conformal generators and the polarization vectors into these combinations here. And then you can start asking a question, well, what happens to the momentum conservation delta function here? And that the answer to that question is very simple by just noticing that that delta function is nothing else but the scalar contact diagram in Minkowski space. So if we just take some point y and then integrate over the bulk of the Minkowski with plane waves attached to the external states, then that gives us a delta function. So similarly, so that gives you an idea how to upgrade that understanding to curved space. The only thing you have to do is take some point y, integrate over the full space, and connect everyone with these bulk to boundary propagators to axis. Okay, so that's nothing but a scalar contact diagram in the sitter. So in conclusion, we propose the following representation. The representation will be that some cosmological wave function of some interacting theory can be expressed as a rational function of our operators as well as some other data, acting all on the scalar contact diagram. So the point of that is that the point of that representation is that all complications are still here in the wave function, but they are all encapsulated by this theory-independent contact diagram. And all theory-dependent information is supposed to be very simple and go outside of that. So that representation is supposed to be useful when you want to compare wave functions in different theories, because then you just have to compare this operator. And that's, of course, what is ideal for double copy, because that follows the same structure. And I should say that that's something that, at least philosophically, is very simple to what people call weight shifting operators, which is something introduced recently in CFTs and also already used by Baumann et al. In position space wave functions. Okay, so the only difference to flat space is that now we have these operators, we can dot them together and we can construct di and .dj, but they no longer commute. However, one special thing is that you can consider these combinations here, in which you take some subset of particles capital I, and then sum over all conformal generators in that subset. And those combinations, once you score them, they would commute if with two subsets I and j, they're either disjoint, like here, or one is contained within the other. And they do not commute if there's some non-trivial overlap, such as here. Okay. So with this information, what we do is we propose our first version of a double copy, which is we'll introduce a world sheet with a potential, and that potential is just a double sum over all dot products of these operators with this logarithmic term. And then we conjecture that once you devise some two integrands, phi left and phi right, that the scattering amplitude can be obtained using this scattering equations formalism in cosmology. So that we're going to have some localizing integral, which localizes on the critical point of that potential. And all that is acting on the scalar diagram, contact diagram. So here in the setup, the scattering equations or the critical points are determined by the solutions of scattering equations, which, there's some non-trivial sum here, and each term by itself doesn't commute. But what you can show is that once you organize them in this specific combination, they start commuting. So it means that everything is working perfectly. And now at this stage, you can ask yourself, well, could it be that operator valued potentials, such as here, have broader applications in other areas of scattering amplitudes? And we've known since recently, from the work of Roerich, Skinner, Casali, Poom, and Sharma, who in different setups showed that very similar structure also appears, that you have these operators, they just have different properties and different physical meanings, but you can apply the same, very similar looking formalism to ADS3 cross CFT2 correlation functions, as well as celestial amplitudes. And I think this is just the beginning, and then we'll find a lot of similar structure in the future. So let's hope for that. For now, we can, once we've answered our order 0 questions, we can move to order 1 question, which is what is the 0th copy? So of course, there's a natural strategy for doing that. Once you know this representation in terms of scattering equations, you just plug in the phi left and phi right to be both the sums over these particular factors. And once you do this, you have to be extremely careful with the fact that now things don't commute. But if you're careful, what you will obtain is that for all multiplicity in all spacetime dimensions, the cosmological wave functions for the Biogenes scalar can be expressed in exactly the way that you might have hoped it would be expressed, as a sum over trivalent diagrams with these propagators. And because of the way that these propagators are defined, they all commute. So it doesn't matter in which way I write it, decorated with the color factors and all acting on the scalar contact diagram. So that's something that normally would have to be computed with this Lagrangian in de Sitter space. So that is the 0th copy. And now we can ask about the other, the gauge and gravity cases. And it's the case in de Sitter space that spinning wave functions are already non-trivial at 3 points. So unlike in flat space, they're no longer fixed by symmetries. So let's look at how this works for pure Yang-Mills. So in pure Yang-Mills, we can separate the structure constant. And here, what we have in our kinematic numerator is that we can dot together epsilon dot epsilon and then epsilon dot d and cyclically symmetrize. So that's one term. And then another term that appears now is that you can contract your epsilon tensors with the structure constant, but now for SOD plus 2. And in principle, these are 2 allowed structures, and the relative coefficient between them is not fixed. So that's something that you need to compute. And if you compute it with Witten diagrams, you find that in general dimension, this is the prefactor. And of course, everything is here acting on the scalar diagram, which at 3 point is very simple. So checking the full double copy is still work in progress, and I hope to report on that soon. But we already know, we have already verified large D limit of these amplitudes. So there's a lot of simplifications there. And what happens is that we can write our gluon amplitude in this way, just from the previous slide, where this n is simply the large D limit of that. So that factor just becomes 3/4. It's still some non-trivial sum over these 2 structures. And surprisingly, it turns out that the 3-point function of gravitons has the double copy structure, in which it is enough to just take 2 copies of that, and at least in the large D limit, everything works perfectly. So you might also notice that double copy for at 3 point is also trivial in 3-dimensional de Sitter, and that's essentially because of the symmetries of CFT2. And at that stage, you might be wondering, well, how about we just investigate CFT2 double copy on its own right, separately? So that's what I'm going to do in the second part of the talk. So for the CFT2 double copy, we consider minimal models. And their minimal models are CFTs in 2 dimensions, which are labeled by 2 integers, p and p prime, which are co-prime. And it's governed by this Lagrangian, which is a free theory, plus some coupling to a background charge. So if you're not familiar with this, just keep in mind the simplest example, when these integers are 4 and 3, this corresponds to the critical Ising model. And the background charge is given by this number. And we also have 3 operators, the identity, spin, and energy operators. And they're just given by some more general versions of minimal modulus operators with a specific charge associated to them. Now we can move on to something called the Coulomb Gas Formalism. So that's something devised by Dotsenko and Fadiev a long time ago, who said that correlation functions in this interacting CFT can be replaced by correlation functions in a free CFT by adding some additional, what they called screening operators. So the background charge is replaced by a given number k of screening operators, and then all you have to do is integrate out over the positions of those operators in a free theory. So the way that you would choose how these screening operators look like and how many of them you have to insert is governed by the neutrality conditions that tell us that the sum of all charges, so the small q are the external charges and capital Q would be the screening operator charges, they have to add up to the total charge for a specific CFT. Or alternatively, you can think about it, thank you, as a charge at infinity. So any correlation function in this language, therefore, can be written as this complex integral over the positions of the screening operators with these potentials, W here, where the W includes interactions between screening charges, the external charges, and the cross terms with the logarithmic dependence. So that gives rise already to what I might call the overcomplete KLT double copy. And that's something that is actually well known, has been investigated in the literature, but by various people over the years, in that the correlation function written in this way can be split as a sum over the holomorphic and anti-holomorphic parts. So these are the conformal blocks for the CFT, weighted with some coefficients. And the number of the terms that you have to sum is basically all allowed permutations. So these coefficients seem to have an interesting interpretation as a 2D S matrix in quotation marks, which is obtained by gluing the surface together in all possible ways. So basically, if in one conformal block you have some permutation tau of the way you would insert them on the boundary, in another one you would have rho, what you might imagine is computing what happens if the punctures, if the permutations are different, they would interact in some way. And the interpretation is that to each interaction point, you should attach a small S matrix, which is basically given by these factors, governed by the charges of the two interacting particles. And then you just multiply them together to get the full R matrix. So that because everything is abelian, it sort of trivially satisfies all the Young-Baxter relations and things like that. However, what you might notice is that these conformal blocks, because we sum basically over all allowed permutations, conformal blocks in this way are hugely redundant. So they're linear dependencies. So what we introduce is a minimal basis for minimal models. And these are bases for all possible models at the same time. And the number of them is given by this fraction. And basically, that's inspired by something that we've known from amplitude literature, in which you can basically, for a given number of screening charges squeezed between the original charges, you can devise this Park-Taylor lag factor. And similarly, you can devise the orthogonal Park-Taylor factor, which is just given by the sums of products of these kind of ratios. So now what we know is that every correlation function can be expanded. So correlation function here on the left-hand side can be expanded in this basis of Park-Taylor integrals, and the coefficients of that expansion would be, you can compute them as intersection numbers. So the advantage of that is that once you express things into this Park-Taylor basis, they seem to satisfy the single valued double copy for all n and for all k. Some special cases of that have been known in the literature previously. And it tells you that these essentially CFT observables can be written as a single valued projection of the conformal blocks as a formal expansion in the small charge limit, at least. And finally, we can move to the KLT double copy, again for all n and k, which tells us that the correlation function in your 2D CFT can be written as this double sum over all conformal blocks with this kernel here. And that kernel turns out to be MCFT, an interesting CFT generalization of the bi-adjoint scalar. And it's computed as intersection numbers of Stashev polytopes or Searchahedron. And there's a very interesting combinatorics there, but I don't have time to discuss that. Let me just flash you one example of the same permutations that we considered before. You can expand it in terms of, in this diagrammatic expansion, as some diagrams where each propagator, instead of propagators factors, it would introduce these combinations, which includes the values of the charges. So the reason why that is not fully a satisfactory double copy yet is that here on the left-hand side, we have something which is an observable and has some well-known physical interpretation. On the right-hand side, we have these conformal blocks, and they by themselves don't have a good, so they're not observables. So it would be very interesting if those factors themselves, if they could be some observables in boundary CFT or something of that sort, but we don't know that yet. So that's an open question.
Okay, if you could come.
So on the final slide, let me just summarize what we've done. And at the beginning, we asked about the double copy for position space observables. So we can ask, well, do position space observables double copy after all? And the fair answer is that we don't know, but we've made some progress in the direction of answering this question, both in the case of cosmological wave functions and also CFT2 correlators. So for the cosmological wave functions, what we've done is we've identified the right variables, or at least one set of variables that is promising towards that direction. We introduced the scattering equations for cosmological wave functions. Using them, we've computed Biogeoid scalar wave functions for all multiplicity and all spacetime dimensions. And we made some early checks for 3-point functions in terms of glue to gravity double copy. Similarly, in the CFT2 correlators, what we've done is we've introduced minimal basis for minimal moles. We proposed a single valued double copy, which double copies observables in terms of conformal blocks. And finally, we explored the combinatorics of the KLT relations and their generalizations of the Biogeoid scalar. So with that, let me thank you for your attention.
Okay, thanks, Sebastian, for this very clear and nice talk. I guess we have time for 1 or 2 quick questions, if there are any.
Alfredo.
Hey, thank you for the talk. I just have a quick question. So what's the specific reason you're calling the partial amplitudes when you do the KLT expansion for the 2D correlators? What's the specific reason you're calling these conformal blocks?
You mean why I'm using these specific conformal blocks?
Yeah, I mean, conformal blocks encode the complete descendant family, right? So do they encode
exactly. So that's exactly what I meant, that we introduced this relation, and for now, these conformal blocks, it might seem arbitrary that we introduce this basis, and it would be very nice if those conformal blocks had some physical interpretation. And we think that, I mean, there might be some things to say there, but we don't have anything concrete to say to answer the question right now.
So you don't know if they are invariant under conformal transformations, like SL2C?
They should be invariant under SL2C, yes.
In which case they wouldn't encode the full descendant family, right?
Yeah, I'm not sure we can discuss this meaningfully for generic for this Park-Taylor basis. So that's still an open question what that exactly corresponds to.
Okay, thank you.
So maybe one more quick question by Piotr, and then the remaining question we can probably defer to after the second
sorry,
talk.
I think, thanks. I think Julio was before me, so I'll ask my question.
Sorry, then Julio.
Okay, thanks, Piotr. Yeah, it's related to Alfredo's question, because there's 2 things that people call conformal blocks. One is the usual conformal blocks in the higher dimensional CFT, which encode the whole family of descendants. And then there's these kind of building blocks of correlators in minimal models, and in higher dimensions, there's also like vectors of partition functions. I think this is in the second sense, right? And typically these things, what they're like correlation functions or partition functions in CFTs, which are chiral. Like if you take like self-dual scalar, for instance.
I guess that's if on the left-hand side you compute partition function.
Yeah, but the theory on the left hand side is modular invariant and it's perfectly healthy, right? Yep. But on the right hand side, these conformal blocks that you, in principle, that could be correlation functions of some theory that is not modular invariant. There's a vector of things here that are mapped under each other under modular transformations, right?
Yeah. And then the question is whether the modular transformation, basically, is it valid on the level of each integral here, or does it only come after you sum? And I don't know how to answer this right now.
But there are theories that we know that they give, like, that their correlation functions are not modular invariant, that they map under each other, which are like chiral CFTs in general. Mm-hmm. Right? So is the guess that these objects will be correlation functions of some chiral CFT? Okay.
Yeah, it sounds like that would be a natural guess. Yes.